Hi everyone, welcome to goclasses. In this session, we are going to discuss functional completeness, complete summary. Okay, all the concepts, all the results, all the important points, everything I will tell you. So this is going to be complete summary of functional completeness. Okay, so let's start. In Boolean algebra, we have already seen many operations, right? We have seen AND operation, OR operation, NOT, NAND, NOR, XOR, XNOR. Okay, so we have seen many operations in Boolean algebra. And using these operations, we can write expression of any Boolean function. If you have any Boolean function, you can write the expression of that Boolean function using these operations. But tell me, is it necessary that we should have all of them? Okay, do we need all these operations to write expression of any Boolean function? So if I give you a Boolean function, then to write the expression of this Boolean function, do we need all of them? Okay, so the answer is no. We don't need all of them. For example, if you have these three, if you have and or not, if you have these three, then you can express any Boolean function. Similarly, using this NAND alone, okay, using this single operation, you can write expression of any Boolean function. Okay, so this is the point. So remember, what is functional completeness? Functional completeness means basically we want to find that set of Boolean operations using which we can write expression of any Boolean function. Means any Boolean function can be expressed using only those operations. For example, these three operations, these are functional complete. Means using these three operations, you can express any Boolean function. This is also functional complete. Using only this operation, you can express any Boolean function. You can write expression of any Boolean function. Okay, so what is our topic? Our topic is functional complete, and this is a set of Boolean expressions using which we can express any Boolean function. Okay, so remember, basically we want to find which set of Boolean operations is sufficient to write expression of every Boolean function. Okay, this type of set of Boolean operations, that will be called functionally complete. Okay, is this clear? For example, you can see or comma not. Let me tell you, this is functionally complete. Means if you want to express any Boolean function, then you don't need all these things. You don't need and, you don't need NAND, you don't need NOR. Okay, what you need? Only using these two, you can write expression of any Boolean function. So that is the reason this is called functionally complete. Functionally complete means you can express any Boolean function using only these two operations. Okay, so this is the simple idea. Now let's move on. So let's see the definition. Functionally complete: a set of logical operations, a set of Boolean operations that is functionally complete if any Boolean expression, any Boolean function can be expressed in terms of only these operations. So remember, if I give you a set of Boolean operations such that every Boolean function can be expressed using only these operations, then these operations will be called functionally complete. Okay, so this is the simple definition. Similarly, in digital circuit, in digital logic, we study many logic gates. We study OR gate, AND gate, inverter, NOT gate, NAND gate, NOR gate, XOR gate, XNOR gate, yes or no? So we study all these logic gates. We study. Now, if I want to implement any digital circuit, then I can create any digital circuit using these logic gates. Yes or no? Now tell me, is it necessary that I should use all of them to create a digital circuit? No. Let me tell you, for example, if you have these two, using these two, okay, if you have these two digital circuit, or I can say if you have these two logical gates, then using these two, you can implement any digital circuit. So what is the point? Remember, these many logic gates we study, but let me tell you, if you want to create any digital circuit, if you want to implement any digital circuit, then these two gates are enough. Even this gate alone is enough. This NAND gate, this one single gate, basically I can say this NAND gate itself is enough. Okay, using NAND gates, what you can do, you can implement any digital circuit. Similarly, this NOR gate is enough. Okay, so very simple point. So the same point we have here. So if you have a set of logical gates which are enough to implement any digital circuit, that will be called functionally complete. Is this clear? Okay, so let's see. You can see, if you have a set of logical gates, if you have a set of digital circuits, okay, this set of logical gates will be functionally complete. We will call it functionally complete if every function you can realize only using these gates. Okay, for example, as I told you that these two gates, look at this, and comma not. These two gates, these are functionally complete. Means every digital circuit you can implement using these two gates. Any Boolean function you can realize using these two gates. So these two gates, I can say these are functionally complete. Okay. Now let's move on. Now let's see our first result, that is and nor and or not. Okay, these three, this set, look at this set. In this set we have three Boolean operations. So this set, this is functionally complete. Okay, this is our first result, that if you have these three operations, if you have these three Boolean operations, then using these three Boolean operations you can implement every Boolean function. Okay, any Boolean function can be written only using these operations. Okay, to express any Boolean function, you only need these three operations. So this set is functionally complete. Can you prove it? Yes, of course we can prove it. But first, let's see this example. Consider this function. Can I write this function expression for this function? Can I write only using or, not, and? Okay, only using these three operations. Can I express this function on your screen? So yes, I can do that. What I can do, you already know that every function I can write as sum of minterms. Okay, this function I can write as sum of minterms. Basically, I can do what I can do to write the expression of this function. I can do some summation of those minterms where the function value is equal to 1. Okay, so basically this function f I can write as a sum of minterms where function value is 1. So you can see here function value 1, function value 1, function value 1, function value 1. So what I can do, this function I can express as a summation of these minterms. Okay, summation of these minterms. So which minterm is this? This is x1 bar, x2 bar, x3. Okay, so this is the minterm, right? This is our minterm. I can say this is our minterm one, right? Correct. Okay, or what I can do, which minterm is this? This is x1, x2 bar, x3. Okay, so this is our another minterm. You can see this is our minterm 4. This is minterm 4. What I can do, or remember summation of all the minterms where function value is 1. So I am doing summation of all the minterms. Which minterm is this? This is a x1, x2 bar, x3. Okay, x1, x2 bar, x3. Or which minterm is this? This is x1, x2, x3 bar. Okay, is this clear? Okay, so you can see this is our minterm 5 and this is our minterm 6. Okay, very simple. So now you tell me, in this expression, are we using anything other than and or not? We are only using or, not, and. Yes or no? For example, here you can see this is our or. Okay, here you can see there is and also. For example, you can see this is the and. Okay, here there is and, right? Okay, see this is and. Okay, so I can say, for example, this is our and, right? Yes or no? So very simple point. And also we are using not. Okay, so what I can say, I can say that here this function I am expressing only using which I am using only. Okay, using only not and or. Okay, is this clear? So this is the point. So remember, this set or, not, and this set is functionally complete. Any Boolean function can be expressed using only these operations. Okay, and this is another example. Okay, so I hope you understood. Similarly, you can also see what you can do. If I give you any other function, then that function also you can express only using or, not, and. Yes or no? Is this clear? So very simple. What is the proof? Let's see this proof, that and or not, this is functionally complete. What is the proof? Let me tell you the proof. The proof is like this, that if you have any Boolean function f, you take any Boolean function f, for that Boolean function we can create the truth table, right? Yes or no? Okay, if you have any Boolean function f, then what we can do, we can create truth table, correct? Okay, we can create truth table of f. And from the truth table of f, what we can do, from here what we can do, we can express this function as summation of minterms where function value is 1. Yes or no? Is this clear? Basically summation of minterms. From this truth table we can express this function as summation of minterms, sum of minterms. Okay, is this clear? And every minterm, that is a product term, right? Yes or no? Okay, look at what is a min term. What is the definition of min term? This is a product term that you already know. Product term containing all the variables. This is the definition of min term. This is a product term containing all variables, containing every variable, containing all variables. But this is a product term, right? Yes or no? Okay, for example, if you have this function f, a, b, c, if you have this function f, then what are the min terms of f? Can you write the min terms of f? Okay, what are the min terms for this function? What are the min terms? Min terms of f, for example, you can see this is a min term abc. For example, this is a min term a bar bc. For example, this is a min term ab bar c. For example, this is a min term ab bar. Okay, like this and so on. So can you notice every min term? Can I say that is a product term containing all the variables? Tell me one thing. Can I say that every min term is basically a combination of not, comma, and? Can I say? Can I say that every min term, basically every min term has only two operations? Every min term has only two operations, either and, comma, not. For example, not, comma, and. Yes or no? There is and also, there is not also. There is and also, there is not also. So you can see every min term contains what? Tell me, contains what? Contains and, comma, not. Yes or no? Is this clear? Okay, if you look at any min term, that will contain and, comma, not only. Okay, now you can easily see that for any Boolean function, what you are doing, you are writing sum of min terms. Okay, you are writing sum of min terms. Then what is happening? Tell me. When you write sum of min terms like mi or mj or mk, okay, like this, if you are writing sum of min terms, then what is happening? Which operations are you using? Tell me. To express this function f, which operations you are using? See, you are using or operation. Okay, you are using or operation, right? Okay, sum of min terms. So you are using or operations. And remember, inside this min term, which operation you are using? Inside this, you are using and, comma, not. Okay, inside this, you are using and, comma, not. Right? Yes or no? Is this clear? Please tell me. Let me know. So this is the idea. So finally, I can say, remember, finally, I can say that to express f, only three operations I'm using. Okay, to express f, only three operations I'm using. I'm using and, not, or. Okay, so this is the proof. This is the proof that and or not, this is functionally complete. Means every Boolean function can be expressed only using these three operations. If you have any Boolean function f, what you do, you create the truth table of f. From the truth table, you can express this function f as sum of min terms. You can write sum of min terms. Okay, and you can notice sum of min terms. Every min term is a product term. So every min term only contains and, comma, not, that we have already seen. For example, this is a min term and it contains only and, comma, not. There is and, there is not. Okay, so min term contains and, comma, not. And when you express this function f as sum of min terms, then overall what we are doing, we are using or and not. Only these three things we are using. Okay, so this is the proof that and or not, this is functionally complete. Okay, is this clear? Please tell me. So very simple. Now let's see the next result, that is and, comma, not. This is functionally complete. Means you don't even need or. Okay, see, our previous result was what? Our previous result was and or not. This is functionally complete. Means using these three operations, we can write expression of any Boolean function. Okay, every Boolean function can be expressed using only these three operations. Now I am saying that we don't need this or. Okay, and, comma, not is enough. Okay, and, comma, not is enough. So this is our another result, that is and, comma, not, that is functionally complete. And can we prove it? Yes, of course we can prove it. Notice we have already seen that and or not, that is functionally complete. Yes or no? This we have already seen that and or not, this is functionally complete. This is functionally complete. Now I am saying that and, comma, not is functionally complete. I am saying that and, comma, not is functionally complete. See why I am saying that this is functionally complete. Okay, this is functionally complete. Why I am saying this is functionally complete? Because using these two, I can create or. Okay, using with the help of and, comma, not, I can create or. Okay, so is this clear? See, already I have and, I have not, and with the help of these two, I can create or. So overall, I can say that I have all these three. Yes or no? If you give me these two, then I can create all these three. Okay, and I can express any Boolean function. I can write expression of any Boolean function. So this is the point that and comma not, this is functionally complete. With the help of this, I can create or. Okay, because we can create or. Tell me how you will create or. Okay, from this, how you will create or. Let me know. Let's see how to create or. Create or. Okay, so let's see how to create or. Very simple. I want to create A or B. So what I can do, remember I have and comma not. These two things I have. So I have negation. So I can use negation. I have negation. I have and. Okay, I have negation. So you can easily see that using and comma not, I can create or. Okay, is this clear? Very simple, right? So very simple point. Remember, we already know that these three operations, this is functionally complete. Now I am saying that we don't need or. Using these two and comma not, I can create or. Okay, so if you give me these two operations, then I already have these two operations, and using these two operations I can also create or operations. So very simple, this set is a functionally complete, means any Boolean function can be expressed only using these operations. Okay, is this clear? Because if I have these two operations, then I can also create the or operation very easily. You can see here, to create the or operation, I am only using and comma not, nothing else. Yes or no? Okay, so very simple. So this is the proof that and comma not, this is also functionally complete. Let's see the next result. The next result is or comma not is functionally complete. Okay, means if you give me or comma not, if you give me these two operations, then I can express any Boolean function. Every Boolean function can be written in terms of only these two operations. Okay, how can you prove it? Again, very simple. If you give me these two operations, then I can create and. Okay, what I can do, from these two I can create and. Can you create and? From these two I can easily create and. Very simple. I want to create and, so what I can do, with the help of only these two operations I can create and. What I can do, I can use negation. Remember, I can use not, I can use or. Okay, I can use not comma or. So very simple. Now you can easily see that with the help of or comma not, I can create and operation. Okay, is this clear? So very simple point. Remember, if you give me these two operations, then I can also create the and operation. And we already know that or and not, that is functionally complete. So this is also functionally complete. Is this clear? Please tell me. So this is a functionally complete. Okay, very simple. Now let's move on. Now our next result, that is NAND operation is functionally complete. Means you don't need anything else. Only this single operation is enough to express any Boolean function. Okay, if you give me any Boolean function, then I can write expression of that Boolean function only using this operation. I don't need anything else. So this NAND itself is functionally complete. Okay, what is NAND, that you already know? Let's see the NAND operation. What is the symbol for NAND operation? This is the symbol, right? Yes or no? Okay, so what is NAND operation? That is A NAND B. That means first you do and then you do negation. Okay, so this is your NAND operation that you already know. Now I am saying that this NAND operation, this is functionally complete. This is functionally complete. Okay, so how to prove it? Tell me. How to prove that NAND is functionally complete? This single operation is functionally complete. Very simple. We can create, we can create not. Okay, we can create not using NAND. Okay, so we can create not using NAND. How to create? Very simple. Okay, if I want to create a bar, then all I have to do, very simple, just do a NAND a. Okay, if I do a NAND a, I will get a bar. Yes or no? So you can see this note I can create, this note I can write in terms of NAND. Okay, very simple. Similarly, I can create, for example, and also I can create. Okay, I can create and using this NAND. Okay, using this single operation, I can create and also. How to do that? So if I want to create and, then what I can do, you can check. Okay, first I can do a NAND b, then again a NAND b. Okay, so you can check it out that this is same as AB. Okay, let me tell you that this is same as AB. If I do this a NAND b, then again I do a NAND b. Okay, let me tell you this is same as AB, because what is a NAND b? That is basically AB whole bar. Okay, NAND, this is basically AB whole bar. And finally, what it will be? Okay, you can easily see this will be AB whole bar, AB whole bar, whole bar. and finally that is basically AB whole bar bar, and that is AB. Okay, yes or no? So you can easily see that this expression is same as AB. Now, did you notice that to write the AND operation, I'm only using the NAND operation? Did you notice? We are only using the NAND operation, nothing else. Okay, so very simple point that I can create AND using NAND. Okay, using this single operation. Okay, what I can do, I can create AND operation. I can also create OR operation. Okay, how to create OR operation? Let's create OR operation using NAND. Okay, that also is very simple. That also is very simple. For example, if I want to create A or B, then you can check. All I have to do, first I create A bar. Okay, NAND B bar. Okay, what I do, A bar NAND B bar. Okay, you can check this is your A or B. Okay, this also you can check. Let me do it here. So you can check that this is A or B. For example, if I do if I do A NAND A, this is A bar that we already know. Okay, A NAND A, this is a A bar. Okay, so we have A bar, then NAND B NAND B. So this is actually, if you notice what this is your A bar that you already know. This is your B bar that you already know. Okay, so finally we have A bar, B bar, NAND, and that is your A or B. Okay, is this clear? So very simple. Okay, is this clear? Please tell me. Okay, so this is the idea. Now, did you notice that this NAND operation alone is enough to create not, we can create and we can create or. Okay, so this is also functionally complete, because if you give me this operation, if you allow me to use only this operation, then I can write any Boolean function. Okay, I can express any Boolean function, because you can see with the help of only this operation, I can create not, I can create and, I can create or. Okay, very simple. So this NAND is also functionally complete. Is this clear? Please tell me. Okay, so now let's see that a NAND gate is also functionally complete. See, NAND operation is functionally complete, so NAND gate is also functionally complete. With help of NAND gate, can you create NOT gate? Okay, let's see this NAND gate. Okay, now let's talk about the NAND gate. Now we will talk about gate. So far we were discussing NAND operation. Please understand. So far this operation we were discussing. Okay, this Boolean function we were discussing. This Boolean operation we were discussing. So you can see this operation. Yes or no? This operation we were discussing. Now we will discuss NAND gate. NAND operation is functionally complete. That we have already seen that NAND operation is functionally complete. Okay, this arrow, this NAND, this is functionally complete. Now we will see that NAND gate is also functionally complete. Okay, see this NAND gate. What is NAND gate? That you already know. This is your NAND gate. Okay, if inputs are AB, then what is the output? Then the output is AB whole bar. This is the NAND gate. Now with the help of NAND gate, I can create NOT. Okay, so can you create NOT gate? Can you create NOT gate? Okay, let's see how to create NOT gate. Remember this NOT gate I can easily create with help of NAND. Okay, this NOT gate, A bar, this NOT gate, what I can do, I can create with the help of NAND. Very simple. All I will do is basically this A, this I will give as two inputs of NAND. And now you can see what I will get. I will get A bar. Yes or no? Basically, if you notice, I will get A bar, and that is same as A bar. So very simple that with help of NAND gate, if you give me NAND gate, if you allow me to use NAND gate, then I can easily create NOT gate. Okay, I can also create AND gate also. Okay, let's see how to create AND gate. Let's see how to create AND gate with help of this NAND gate. Very simple. So if I want to create this AND gate, this is A, B. Okay, output is AB. Now very easily I can create, and that will be like this. Okay, what I can do, I can create like this. So first I will give this AB, okay. Then the output will be what? Output will be AB bar. Now what I will do, now I will use another NAND gate. Okay, and now the output will be AB. Okay, so remember, if I want to create AND gate with help of NAND gate, then two NAND gates I need. Yes or no? How many NAND gates I need? So I need two NAND gates. Is this clear? Okay, so I need two NAND gates. Is this clear? Can you create OR gate with the help of NAND gate? Tell me. Can you create OR gate? Let me know. Can you create OR gate with the help of NAND gate? Yes, of course, that also I can do. Okay, so remember this OR gate, if I want this OR gate, means A or B. Okay, so what I can do, with help of NAND gate, I can create this. Okay, how I will do this? Very simple. The idea is this, that basically you already know that first I will create A bar, then I will create B bar, and A bar NAND B bar, that is what? A bar NAND B bar, that is your A or B. Okay, so what I will do, remember, I will create A bar, I will create B bar, and then I will do NAND. Okay, so this is what I'm going to do. I will do NAND. Basically, the idea, let me tell you the idea. The idea is like this, that I will do NAND of A bar B bar, of A bar B bar, right? Okay, now remember, now I can create this A bar using NAND, yes or no? I can create this A bar using NAND very easily. Okay, so using NAND, I can create A bar very easily. So this is how you can create A bar. This will give you A bar. And similarly, I can create B bar. This will give you B bar. Okay, and finally, what I can do, I can use another NAND gate, and this will give me A or B. Okay, is this clear? So tell me, to create OR gate, how many NAND gate I need? I need 3 NAND gate. I need 3 NAND gates to create OR gate. If I want to create OR gate, then I need 3 NAND gates. So like this. So remember, NAND gate is universal gate. Universal gate means this is single gate. This single gate is enough to create any Boolean function, to implement any Boolean function. Okay, universal gate simply means this is functionally complete. This single gate is functionally complete. Okay, so this is the word we use, universal gate. Remember, universal gate we use when a single entity is enough to implement any Boolean function. So you know that this single NAND gate, this is enough without help of any other gate. We don't need any other gate. We don't need inverter. We don't need OR gate, AND gate. We don't need those things. Okay. This NAND gate is enough to implement any Boolean function. So this is called universal gate. This is the reason this is called universal gate. Is this clear? Similarly, the next result, that is NOR operation and NOR gate, these are also functionally complete. Okay. These are also functionally complete. Let me tell you. See this NOR operation. First, we will talk about NOR operation, then we will talk about NOR gate. NOR operation, this is the symbol. Okay. Now, this is functionally complete, this NOR operation. First of all, what is NOR operation? A nor B. That means first you do OR, then you do complement. So this is your NOR operation. Now, I am saying that this NOR operation is functionally complete. What it means? This this single operation is enough to write any Boolean function, to express any Boolean function. Only this NOR operation is enough. With help of NOR operation, we can write expression of any Boolean function. Okay, so can you create not? Can you create not operation? Tell me. Can you create not operation? For example, this A bar. Can you create this A bar with help of NOR? Yes, of course. Very simple. A NOR A. That will give you A bar. Okay. Can you create OR operation? Can you create this OR operation? A or B? Can you create this? Tell me. Yes, I can also create A or B. Very simple. Just check this. A NOR B NOR A NOR B. Okay, you can check this is your A or B. Okay, see what I'm saying. Look at this. A nor B nor A nor B. Okay, let's see that this is actually A or B, because what is this? This is your A or B whole complement. What is this? This is A or B whole complement. Okay, so finally, if you notice, what you will get? You will get A or B whole complement nor A or B whole complement, and finally what you will get? You will get A or B whole complement, or A or B whole complement, and that will be A or B complement, and that is A or B. So you can see this equation is actually giving you A or B. Is this clear? So very simple. This OR operation we can write only in terms of NOR operation, like this. Can you create AND operation? Can you create AND operation? Yes, of course, that also I can create. If I want to create AND operation, very simple. First, I will create A bar. This is like A bar nor B bar. Okay, A bar nor B bar. This will give me AND. Okay, see what I'm saying? I'm saying that A bar, you already know that A bar nor B bar. What that will give you? That will give you Okay, if you apply the De Morgan law, that will give you A and B. Okay, so this is what I'm saying, that now this is very simple. Basically, this is A nor B, nor B nor B. Sorry, A nor A, nor B nor B, and this will be same as AB. Okay, so like this, very simple. Okay, is this clear? So you can see that NOR operation is functionally complete, because with help of NOR operation, I can create NOT operation, OR operation, AND operation. All these operations I can create. So this is functionally complete. Okay, is this clear? Now, similarly, this NOR gate is also functionally complete. Okay, look at NOR gate. Let's look at NOR gate. This is also functionally complete. And this is universal gate. Means if you only have these gates, NOR gate, okay. If you don't have any other gate, if you don't have OR gate, AND gate, inverter, okay. If you only have these gates, NOR gates, if you have, then with the help of these gates, you can implement any digital circuit. You can realize any Boolean function with the help of only NOR gates. So this is functionally complete. How to check this is functionally complete? This is your NOR gate, right? This is our NOR gate A, B. So NOR means A, B whole bar. This is NOR. Now what you can do, you can create NOT gate. Okay, very easily we can create NOT gate. Let's see how to create NOT gate. Okay, so this NOT gate I want to create, this inverter I want to create. So very simple, what I can do, just use this NOR gate. Okay, and this A you give as two inputs. Okay, this same input you give, basically this same input you give. Okay, what you will get, you will get A bar. Very simple. Next, you can create OR gate also. From NOR you can create OR gate also. I want to create this OR gate, that also I can do. Okay, how to do that? Very simple, just use this NOR gate two times. Okay, use this NOR gate two times. Very simple. Okay, put AB, then use this two times. Remember, the output will be A or B bar. Okay, and here the output will be A or B. Okay, very simple. So just use this NOR gate two times. So remember, two NOR gates are required. Two NOR gates are required to create the OR gate. Okay, similarly, you can create the AND gate also. Okay, what you can do, you can create AND gate also with help of NOR gate. So to create the AND gate, this AND gate I want to create A, B, A, B. Okay, so if I want to create this is very simple. The idea is like this. First, I will create A bar, then I will create B bar, and what will be their NOR? A bar, B bar, NOR. That will be same as AB. Okay, because you can easily see that will be same as A or A bar or B bar whole bar, and that is same as AB. Okay, so this is the idea. This is the idea. So this idea I am going to implement. Okay, what I'm going to do, I will create A bar, I will create B bar, and then I will put the NOR gate. Okay, so this is what we are going to do. First, I will create the A bar. Okay, remember, this will give me A bar. This will give me A bar. Then I will create the B bar. Okay, then I will create the B bar. This will give me B bar. And then I will put another NOR gate. Another NOR gate I will put. And finally, I will get AB. Okay, so you can see, to create AND gate, I need three NOR gates. Okay, is this clear? Please tell me. So you can see NOR gate is also functionally complete. With help of NOR gates, I can create AND gate, NOT gate, OR gate, all these things I can create. So any Boolean function can be realized only using NOR gates. So this is also universal gate. Okay, if you only have NOR gates, then using that you can realize any Boolean function. Okay, so remember, NAND comma NOR gates, these are universal gates. Also, we have seen that OR comma NOT is functionally complete, OR comma AND is functionally complete. Sorry, NOT comma AND is functionally complete, and NOT comma OR is functionally complete. So this is what we have seen so far. I hope you understood the idea of functionally complete. Okay, so the definition of functionally complete, the idea of functionally complete, did you understand? Okay, everything we have seen so far. Okay, NAND gate is universal gate, means this is functionally complete. NOR gate is universal gate, means this is functionally complete. This set is functionally complete. This set is functionally complete. So this is what we have seen so far. Okay, universal gate, that simply means functionally complete. Okay, this is another, basically this is functionally complete. This simply means that it is functionally complete. Actually, this word is used for those gates which alone are enough. Okay, actually this is used for those gates which alone are enough to realize any Boolean function. Okay, for example, NAND gate alone is enough. Yes or no? If you only have NAND gates, then using those, you can basically realize any Boolean function. Okay. Anyway, universal gate, basically this is just a another word for functionally complete. Okay. Now let's move on. Now let me ask you this question. Given a set of logical operations S, if I give you a set of Boolean operations, okay, how can you determine is it functionally complete or not? Okay, if I give you some set of operations, I give you, and then how can you determine that this S is functionally complete or not? How you will determine? Tell me. Very simple. If I give you any set of logical operations, any set of Boolean functions I give you, and I ask you, is this functionally complete or not? Very simple. What you can do, you can either you can create or comma not, yes or no. What you can do, if we can create, please focus, from this s, okay, from this s, if we can create or comma not, can I say s is functionally complete? From s, if I can create these, then can I say s is functionally complete? Yes. Okay. Similarly, from s, if I can create not comma and, then s is functionally complete. From s, if I can create NAND, then s is functionally complete. From s, if I can create NOR, then s is functionally complete. Okay. Is this clear? So this is the answer. If we can create either this or NAND or NOR from s, then s is functionally complete. Okay. Very simple. Let's see this question. Prove that this set implication comma negation, prove that this is functionally complete. Okay, first of all, let me tell you that this is implication. Okay, what is this? This operation is implication. Implication, and it is like this: A implies B. Actually, this is same as A negation or B. Okay, these are same. Okay, A negation or B. Let me tell you, this implication is like this. In propositional logic, in discrete mathematics, we study implication. But let me tell you the truth table. The A implies B. This is the truth table. Okay, 0, 0, 0, 1, 1, 0, 1, 1. The truth table is like this. This is the truth table of implication. Okay, so this implication, in simple words, this A implies B. This you can write as A bar or B. Okay, so like this you can write A bar or B. This is your implication. Now implication comma negation, that is functionally complete. So tell me, if I want to prove it, then what I need to do? What I need to do? Implication comma this implication comma not is functionally complete. If I want to prove it, then what I will do? I will try to create from this set. Can I create or comma not? Okay, see what I will do. From this set, if I can create or comma not, if I can create or comma not, then can I say that this will be functionally complete? Tell me. If I can create or comma not, let me know. From this set, if I can create or comma not, then can I say this will be functionally complete? Yes. Okay. Now this we already have, not we already have, right? Yes or no? Not we already have. So we only have to create or. Okay, let's see how to create or. We want to create A or B. And what we have? We have implication comma not. Okay, two things we have. So only using these two things, only using not comma implication, we have to create this or operation. So how can you do this? You already know that A implies B, that means A bar or B. Okay, I want to create A or B. I want to create A or B. So very simple, what I can do? I can do A bar implies B. Yes or no? Look at this. Here, I'm using only not comma implication. Did you notice what I'm using? I'm using not comma implication only. Only two operations I'm using here. Only two operations. Those are implication comma not. So with help of implication comma not, I can create or operation. Okay, so if you give me these two operations, I can create or operation. Already not operation is already there. So can I say this is functionally complete? Yes, this is a functionally complete. Is this clear? Please tell me. So very simple point. So we can say that this implication comma negation, this is functionally complete. Is this clear? Let me know. Please tell me. Is this clear? Okay, tell me. Okay, now this is my question. Create and. Can you create and from from implication comma negation, implication comma not? Okay, because we have already seen this is functionally complete. We have already seen this is functionally complete. If this is functionally complete, then you must be able to create and. can you create and with help of only these two? Can I do that? I want to create and with help of only these two operations. Only these two operations you can use. You cannot use any other operation. So can I do that? Tell me. Yes. See, this is the idea. If I want to create AB, then what I can do? I can do A bar or B bar whole bar. Yes or no? I can do A bar or B bar whole bar. So very simple. What I can do? I can do like this. Look at this. A implies B bar whole bar. Okay. That's it. Tell me, what is this? Let me know. What is this? That's it. See, A implies B bar whole bar. Okay. This is a whole bar. And what is this? This is A bar or B bar. And that is same as AB. Yes or no? So did you notice I can create AND gate with help of only these two operations, implication comma not. See, I'm using implication comma not. I'm not using anything else. Okay, so this is how I can create AND gate also. This AND operation also I can create with help of only these two operations. So this is the final result that this is functionally complete. Yes or no? Is this clear? Please tell me. Very simple. Tell me the answer for this question. XOR comma 0. Okay, here you have two functions. You have XOR function and you have this constant 0 function. Is this functionally complete? How you will prove it? Tell me what you will do. I need to create, what I will do? I will create not comma or I will create not comma and. Yes or no? Is this clear? See, I will create either not comma or I will create not comma and. Okay, so tell me how to create. Can I create not first? Let's see how to create not. Can I create not first? How to create not? We already have XOR, right? What is XOR? That we already know. A XOR B, that is A bar B or AB bar, that we already know. Okay, so how to create not? Only these things I can use. I can use XOR comma 0. Only these two things I can use. Okay, so what I can do? Let me check. A XOR 0. Will it work? Will it work? What is A XOR 0? I can use only XOR comma 0. So will it work? It will be, okay. I want to create not. See, I want to prove this is functionally complete or not. So either I can create this combination or I can create this combination, right? Yes or no? Okay. I can create this combination or I can create this combination. So let me try to create not. Okay. How to create not? Tell me. Okay. Is it working? A XOR 0. What is that? That is actually A. Okay. That is actually A. So, okay. Is there any way, for example, if I do A XOR A, that is 0. Can I create A bar? Tell me. Can you give me any way to create A bar? I want to create not. Can I create not? Tell me. Let me know. Please tell me. Can I create not? I want to create not. Is there any way to create not? See, if I do this, I cannot create A bar. If I do this, I cannot create A bar. Okay. So, is there any way? We cannot create not. Okay. Yes or no? If you think about it, okay, just think about it. Okay. Maybe multiple times using this, can I create not? By using this XOR multiple times, can I create not? Is it a possibility? By using this multiple times, can I create not? Actually, you can check many possibilities. For example, will this give me not? Okay, if I do this, will this give me not? This actually will give me 0. Okay, this will actually give me 0. So are you getting my point that actually if you try, okay, try, okay, try, then you will see that you cannot create not. Okay, create not possible. Create not possible. Just try something. Okay, maybe using this multiple times. Okay, maybe like this. Can I create A bar? Can I create A bar? Okay, this is not possible. But I want to ask you one thing. Are you getting a confidence that okay, this not is never possible? See, you are checking some combinations, maybe three things you have checked, but maybe using this four times, using these two combinations, okay, basically many other combinations you will have to check, yes or no, in your mind. What will be going on in your mind? It will be going on, maybe there is some other way I can create not. Are you getting my point? Yes or no? In your mind you are thinking maybe there is some other way, maybe there is some other way. For example, maybe something like this I can create. Yes or no? Actually this also will be zero, actually this also will be zero. So in your mind you are thinking that maybe there is some way to create not. But let me tell you there is no way to create not. Okay, so tell me in this method, of creating this in this method, do you get 100% confidence in this method? Let me know. Do you get 100% confidence? No. Okay, because in your mind you are thinking maybe there is some other way to create not operation. But actually after some time I will tell you, don't worry, after some time I will tell you that this is not functionally complete. Okay, with confidence, with 100% guarantee I will tell you that this is not functionally complete. So is this functionally complete? The answer is no. Okay, you can see, you can try some combinations, you can try to create this a bar, but you cannot create a bar. Okay, you cannot create a bar. Is this clear? A bar is not possible. So this not is not possible. Okay, this is the idea. Now let me ask you this question. Let me ask you this question. Is this functionally complete? Is the following set of connectives functionally complete? These four connectives are given to you, four operations are given to you. Is this functionally complete? What you will do? You already have or, comma, and. What you will do? Tell me what you will do. You already have or, you already have and. You will try to create not. Agree? What you will do? Tell me. You will try to create what? You will try to create not. Agree? Yes or no? This is what you will do. You will try to create not. Means you will try to create a bar. This is what you will try to create. Now tell me one thing. How much time you will check? How much time you will try to create a bar? Okay, you will keep trying to create a bar. Maybe there is some way to create a bar. You will check like this. Okay, maybe this will give me a bar. Actually this will also not give me a bar. Then you will check, maybe this will give me a bar, this is also not giving you a bar. Okay, so then you will just check some combinations, some things you will check, yes or no. Basically, for example, okay, using these two you will try to create a bar, using these two you will try to create a bar, using these three you will try to create a bar, using these three you will try to create a bar, using all four you will try to create a bar. Okay, you will keep doing, you will keep doing, you will keep doing, right? Yes or no? Actually let me tell you, after some time you will see this. Let me tell you, you cannot create a bar. Okay, take my word for granted, you cannot create a bar. You cannot create you cannot create a bar. Actually this is not functionally complete. Okay, we will see, don't worry. Actually this is not functionally complete, you cannot create a bar. But my question is how much time you will waste to try to create a bar? Actually this is not functionally complete, you cannot create a bar, you cannot create a bar. After some time I will tell you, you cannot create a bar, this is not functionally complete. But tell me, if you try to create a bar, then will you ever get confidence that you cannot create it? Okay, you will check some combinations, some combinations you will check. Okay, yes or no? You will check these two, using these three, using these four. Okay, you will keep checking, but you will never get confidence that you cannot create a bar. Is this clear? So okay, now we need some concrete way of finding if a given set of Boolean functions is functionally complete or not. Yes or no? Okay, you might be thinking, sir, is there any concrete way? Is there any 100% guarantee way such that I can check functional completeness or not? Given a set of Boolean operations, given a set of Boolean connectives, is that functionally complete or not? Is there any 100% way? Is there a 100% guarantee way? The answer is yes, there is. Okay, and that is Emil Post functional completeness theorem. Okay, so now we will see this Emil Post functional completeness theorem. We will see. Let me tell you, this theorem is 100% guarantee for answer. Okay, this will give you 100% guarantee of yes or no answer. Is this clear? So this is our next topic, that is Emil Post functional completeness theorem. Okay. So this theorem we use for what? This theorem we use when a set of Boolean functions are given to us and we have to determine whether this is functionally complete or not. Okay, so to determine if a set of Boolean functions, if a set of Boolean operations is functionally complete or not, this theorem we can use. Okay, so what is the input? The input is set of Boolean functions. Okay, so let's assume our input is set of Boolean functions, that is f1, f2, f3. Like this, some set of Boolean operations are given to you. Okay, now what we need to do? We need to determine, remember, we need to determine whether this set of Boolean function is functionally complete or not. So these are the steps. The first step is minimize the function and remove all the useless variables. Okay, first what you do, you minimize the functions. Okay, all these, for example, this f1, f2, f3, these functions you minimize, remember, and remove all the useless variables. What are the useless variables? For example, if I give you this function, look at this function, a or ab. Here, can you notice this b is useless? Okay, in this, actually b is useless. Why? Actually, here b is useless. What is the reason? Useless, or you can call it dummy. Actually, here b is useless because you already know that this is same as a. So this function doesn't depend on b. Yes or no? This function doesn't depend on b. This function doesn't depend on b, so you can say that b is useless. Okay, so your first thing is first remove these useless variables. Okay, finally, okay, remove useless variables. Remove these useless variables. Okay, is this clear? So first you remove useless variables, and after removing useless variables, what we are getting? Now we are getting only f a equal to a. Okay, this is we get, right? Yes or no? So remove useless variables. Very simple point. So this is the step one. Okay, is this clear? The step one. If a set of Boolean functions are given to you, this set of Boolean functions f1, f2, f3, and the question is asking, is this x functionally complete or not? Then the first step is minimize these. Okay, minimize them and remove all the useless variables. If there is useless variable, then remove those useless variables. Okay, for example, here b is useless variable because this function does not depend on b. So you can just remove this b. Okay, remove this b. This is what you will get. Very simple. Now, after minimizing, after removing all the useless variables, 5 properties you need to check. And these are simple properties. Okay, 5 properties you need to check. So check the following 5 properties. Now let's see what are these 5 properties. Let me tell you the first property to check, that is zero preservation. Zero preservation. Zero preserving function. Okay, this is our first property. Okay, property one to check, that is zero preserving function. What is zero preserving function? Any Boolean function is zero preserving. Okay, any Boolean function, any Boolean function f. Okay, for example, f a b c. Okay, any Boolean function is zero preserving. When can I say this is zero preserving? What is the definition of zero preserving? When can I say this is zero preserving? Any Boolean function is zero preserving if and only if, okay, when I replace all the variables by zero, then the result must be zero. Is this clear? The name itself is telling you zero preserving. Means when I replace all the variables by zero, the result must be zero. The function value must be zero. If I replace all the variables by zero, then the function value must be zero. This is the definition of zero preserving function. Okay, so this is the first property you need to check. Is this clear? Property one to check. Just check the zero preserving functions. Now let me tell you the result. The result is, if every function is zero preserving, then if, okay, in this x, remember what is this x? X is like this, f1, f2. X is set of Boolean functions, right? Okay, now you can see that if every function, remember, if every function fi in x is zero preserving, is zero preserving, is zero preserving, then what will happen? Then x is not functionally complete. Then x is not functionally complete. Okay, yes or no? Very simple theorem. See, what you need to do, just check, okay, these functions, are they zero preserving or not? This is your set x. and the question is asking this set X, is this functionally complete or not? So what you will do, you will check, is this zero preserving, is this zero preserving, is this zero preserving? If every function is zero preserving, then you can say that this set X, this is not functionally complete. Okay, is this clear? So for example, tell me which functions are zero preserving. Among the standard functions, which functions are zero preserving? Tell me. Give me some examples of zero preserving functions. Zero preserving means if you replace all the variables by zero, the result must be zero. So can you tell me some zero preserving functions? Yes, for example, AND is zero preserving function, OR is zero preserving function, XOR is zero preserving function. Yes or no? Are you getting my point? See, XOR is zero preserving. Why? This A XOR B. This is zero preserving. A is a zero preserving. Why this is zero preserving? This is zero preserving because if I replace all the variables by zero, the result is zero. Yes or no? Very simple. So AND or XOR, these are zero preserving functions. Okay. Yes or no? Is this clear? For example, FA equal to A. This is also zero preserving. This is also zero preserving. If I replace all the variables by zero, I am getting zero. Okay. So these are some zero preserving functions. Tell me, not zero preserving functions, what are those? Can you give me some examples of not zero preserving functions? What are the examples of not zero preserving functions? For example, XNOR. XNOR is not zero preserving function. Okay, yes or no? For example, not is not zero preserving function. For example, NAND. This is not zero preserving, nor this is also not zero preserving. Okay, what about implication? What about implication? Implication is also not zero preserving. Okay, implication. You already know A implies B. That simply means A bar or B. You can see if I replace every variable by zero, the result is not zero. Yes or no? Is this clear? For example, this XNOR, this is not zero preserving. Why? Because what is zero XNOR zero? That is actually one. Okay, yes or no? Zero XNOR zero, that is not zero. Similarly, here also, zero bar is not zero. Okay, so these are not zero preserving function. Did you understand the definition of zero preserving function? Zero preserving means very simple. The name itself is telling you a function is zero preserving if I replace all the variables by zero, then the result should be zero. Then you can call it zero preserving function. And this result is important, that if every function is zero preserving, then X is not functionally complete. Is this clear? Okay, let's move on now. Now let's see the next property to check. What is the second property to check? That is one preserving. That is a one preserving. Tell me the definition of one preserving function. Very similar to zero preserving function. What is the definition of one preserving function? F is one preserving. If I give you, for example, F ABC, F is one preserving. When can I say F is one preserving? F is one preserving if and only if I replace all the variables by one. One preserving. If I replace all the variables by one, then the result must be one. Then you will call it one preserving function. If I replace every variable by one, then the result is one. This type of function is called one preserving function. Is this clear? For example, can you give me which are one preserving function and which are not one preserving function? Tell me one preserving functions. Let me know. And which are not one preserving functions. One preserving function. For example, AND is one preserving, OR is one preserving, right? Yes or no? They are one preserving functions. Okay, you can see here, if I replace every variable by one, then the result is one. Here, if I replace every variable by one, then the result is one. See the definition of one preserving function. A function is one preserving if and only if I replace every variable by one, then the result must be one. This is the definition of one preserving function. So you can see AND, OR, these are one preserving function. For example, XNOR, this is one preserving function. A, this is one preserving function. Implication is one preserving function. So these are one preserving function. What are not one preserving functions? For example, A bar is not one preserving. For example, XOR. XOR is not one preserving, right? Yes or no? Is this clear? For example, Nand is not one preserving, nor is not one preserving, like this. Okay, I hope you understood. Very simple. Now let's see the result number two. The result number two is if every function is one preserving, okay, this is your set X. X is a set of functions, yes or no, set of Boolean functions. Okay, if every fi is one preserving, then X is not functionally complete. This is the result. Very simple result, that if every fi is one preserving, okay, if every fi is one preserving, then X is not functionally complete. Okay, X is not functionally complete. Is this clear? Okay, if each of them is one preserving, then X is not functionally complete. Very simple. Now, do you remember this example I took? Okay, just I took this example, that and, or, implication, and by implication. By implication means ignore. Okay, by implication means ignore. This by implication, this is same as by implication. Okay, did you remember this was not functionally complete? Now tell me, is this functionally complete? Is this a functionally complete? Is X functionally complete? Tell me. The answer is no. Why? You can see all of them are one preserving. Okay, yes or no? All of them are one preserving. All are one preserving. All are one preserving. Yes or no? Please tell me. Did you notice? All are one preserving. And is one preserving. You can see this and is one preserving. One and one is one. Or is one preserving. Implication is one preserving. XNOR is one preserving. So did you notice all are one preserving? And this is the result. This is the result. If every function is one preserving, if every fi is one preserving, then X is not functionally complete. Yes or no? So here you can see, because all are one preserving, all are one preserving, so X is not functionally complete. Now tell me, now did you find that this theorem is very, very simple? Yes or no? Very important, because many complicated questions very quickly you can solve. Yes or no? This type of question. If you remember this example we have already taken, and I told you that if you try to create knot using these four operations, with the help of these four operations, if you try to create knot operation, you cannot create. Okay, you will keep checking the possibilities. You will keep checking the possibilities, but you will not be able to create knot. And I told you that now you can get 100% confidence that your answer is correct, because all of them are one preserving. So I can say this X is not functionally complete. Yes or no? Is this clear? Very simple. Now let's move on. What is the property number 3 to check? What is property number 3 to check? That is self-dual. That is self-dual function. Okay, you already know what is self-dual function. In our lectures we have seen self-dual function means f is self-dual. F is a self-dual if and only if f is same as f dual. Okay, this type of function is called self-dual function, that we have already seen in our lectures. Now let me tell you the result. The result is, if every function is self-dual, then X is not functionally complete. This is your set X. This is set of Boolean functions, right? Yes or no? Set of Boolean operations. Now I am saying that if every fi is self-dual, if every fi is self-dual, then X is not functionally complete. Then this is not functionally complete. Means if each of them is self-dual, then X is not functionally complete. This is another very simple result. Yes or no? Is this clear? Now let's see the next property to check. The next property to check, that is linear. Okay, this next property to check, this is a linear function. This is linear function. Okay, or this is called alternating function. This is called alternative. Okay, anyway, don't worry about it. This is linear function. Okay, so what is linear function? Let's see. This is the next property to check, that is linear function. Okay, now I will tell you the definition of linear function, then we will see the result. Now let's see the definition of linear function. Okay, before you check whether a function is linear or not, first you remove all the useless variables. Okay, so remember, first remove all useless variables. First, remove all useless variables. Okay, if there is any useless variable, then first you remove it. Is this clear? First, remove all useless variables. Okay, after removing all the useless variables, this is the definition of linear function. Let's see the definition of linear function. A function is linear if this happens or this happens. Okay, so either this will happen or this will happen, then the function will be called linear. Now, what the definition? Look at the definition. A function is linear if this happens. That means for every one value of f, wherever f is 1, the number of ones in the input is odd, and for every zero value of f, the number of ones in the input is even. Or for every one value of f, the number of ones in the input is even, and for every zero value of f, the number of ones in the input is odd. See, this definition is actually very simple. Let's see what this definition is saying. This is saying that f is linear. Okay, f without any useless symbols. First, you remove all the useless symbols, all the useless variables. Remember, first remove all the useless variables. Now, when can I say f is linear? F is linear if and only if either this can happen or this can happen. See, remember, either this can happen or this can happen. Either this will happen or this will happen. Now, what I'm saying f is linear if and only if, okay, for all, what should happen? Either this should happen, that for all f equal to 1 rows, for all f equal to 1 rows, okay, the number of ones in the input, number of ones in the input is even, number of ones in the input. Basically, you just have to check number of ones in input. Number of ones in input is even, and and for every f equal to 0 row, for all f equal to 0 rows, what should happen? Number of ones in the input is odd. Okay, number of ones in input is odd. Okay, so remember, function is linear if this happens, this entire thing happens. Okay, this entire thing happens means for all f equal to 1 rows, the number of ones in the input is even, and for all f equal to 0 rows, number of ones in the input is odd. Okay, or what can happen, or this can happen, that for all f equal to 0, for all f equal to 1 rows, for all f equal to 1 rows, number of ones, number of ones in input is odd, and and for all f equal to 0 rows, number of ones in input, number of ones in input is even. Okay, so very simple. Okay, f equal to 1 rows means where function value is 1 in the truth table. Okay, in the truth table where function value is 1. So very simple, this function is linear if this happens or this happens. Please understand, function is linear if this happens or this happens. Means you look at the truth table. In the truth table, look at the truth table. If and only if in truth table, I can say in truth table. Okay, is this clear? In truth table, just look at the truth table. In the truth table, for all f equal to 1 rows, number of ones in the input is even, and for all f equal to 0 rows, number of ones in the input is odd. Or this can happen, for all f equal to 1 rows, number of ones in the input is odd, and for all f equal to 0 rows, number of ones in the input is even. Is this clear? Please tell me. Let me know. Let's see quickly some examples. For example, what about XOR? Is that linear? Can I say XOR is linear? Yes, XOR is linear. Okay, let's check it. A, B, 0 0 0 1 1 0 1 1. Okay, let's create A XOR B. This is A XOR B. Now you check, is this linear or not? Okay, what you will check? See, wherever f is 1, okay, look at this. For all f equal to 1 rows, what are the f equal to 1 rows? These are f equal to 1 rows, correct? Okay, correct. Yes or no? For all f equal to 1 rows, tell me how many ones are there in the input? For all f equal to 1 rows, how many ones are there in the input? In the input, how many ones are there? See, odd number of ones, odd number of ones. In this input, there is only one, so that is odd. In this input, there is only one, so that is odd. So you can easily see that for all f equal to 1 rows, number of ones, number of ones in input, that is how much? How many? Number of ones in input, that is odd. So what should happen? So what should happen? For all f equal to 0 rows, what should happen? So for all f equal to 0 rows, these are f equal to 0 rows. For f equal to 0 rows, what should happen? Number of ones should be even. Yes or no? Is number of ones even? Number of ones should be even. Number of ones in the input, that should be even. Okay, are you getting even number of ones? See, for all f equal to 0 rows, here you have even number of ones. Actually, here there is no one, means there is 0, 1, and 0 is even number. So even number of ones. Here also even number of ones. So this is linear. Yes or no? Is this clear? Please tell me. So XOR is linear. Is this understood? Because this condition is satisfied. Okay, you can see that this is satisfied. Okay, for the XOR function, this is satisfied. Please understand. For XOR function, this is satisfied. So XOR function is linear. Okay, is this clear? What about AND? What about AND? Is this linear? AND is not linear. Okay, why AND is not linear? You can easily check A, B. Okay, let's check AB. 0, 0, 0, 1, 1, 0, 1, 1. This is 0, 0, 0, 1. This is AND. Now you tell me. Okay, this is actually not linear. Why? What is the reason? You can see for all f equal to 1 rows. Okay, just look at for all f equal to 1 rows. Tell me for all f equal to 1 rows, what is happening? For all f equal to 1 rows, this is f equal to 1 row. Number of ones, that is even. Yes or no? Number of ones in input, that is even. Yes or no? So what should happen? So what should happen? Tell me. So this should happen that for all f equal to 0 rows, what should happen? So for all f equal to 0 rows, what should happen? Number of ones in the input should be odd. Number of ones in input should be odd or not? Should be odd. Are you getting odd? For all f equal to 0 rows, these are f equal to 0 rows, f equal to 0, f equal to 0, f equal to 0. In the input, are we getting number of ones odd? Here number of ones is odd, here number of ones is odd, but here number of ones is even. So this is violated. Yes or no? This is violated. Okay, this is violation. So that is the reason AND is not linear. Is this clear? Please tell me. So did you understand the linear function definition? Did you understand? Let me know. Let me know, did you understand? So this is the idea of linear. Okay, so let me tell you which are linear, which are not linear. You can check. You can apply the definition and check. Let me tell you which are linear functions and not linear functions. Okay, linear functions, for example, A, this is linear function. A bar, this is linear function. Okay, A is linear, A bar is linear. Okay, for example, XOR is linear. XOR is linear. You can check XNOR is linear. Okay, these are linear functions. Okay, let me tell you one more thing. This is important. Constant function is linear. This constant function 0, constant function 1, these are also linear. Okay, these are also linear. Constant functions are linear. Is this clear? So this is a note. Not constant functions are linear. Constant functions. Constant functions means 0, 1. These are linear. Okay. What are not linear functions? What are not linear functions? Not linear functions. For example, your AND is not linear. You can check OR is not linear. Okay. You can check. You can check implication is not linear. Okay. You can check NAND is not linear. NOR is not linear. Okay. These functions are not linear. Is this clear? Please tell me. You can check. Just apply the definition and check. Okay, nothing complicated. You just have to apply the definition of linear function. You can see that actually these will be linear. Remember, the constant functions are linear. Okay, this is a note that constant functions are linear. Okay, is this clear? Just apply the definition and check. And this is the conclusion. You can check. You can check Nand is not linear. You can check implication is not linear. Okay, let me check this implication. Is it linear? What about implication? Is it linear? Implication is not linear. Okay, let's check. First of all, what is implication? That you already know, that A, B, implication is like this. A implies B, that is same as A bar or B. Remember, this is same as A bar or B. Please understand. Implication means A bar or B. Okay, so 0, 0, 0, 1, 1, 0, 1, 1. This is implication. Now tell me, is this linear? This is not linear. Why this is not linear? Because check, for all f equal to 1 rows, what should happen? For all f equal to 1 rows, here f equal to 1, here f equal to 1, here f equal to 1. For all f equal to 1 rows, number of ones in the input, is that odd? Is that even? Tell me, for all f equal to 1 rows, for all f equal to 1 rows, number of ones in the input, tell me. Number of ones in input, is that odd? Can I say that is odd? Can I say that is odd? For all f equal to 1 rows, can I say number of ones in the input is odd? No, I cannot say. Here number of ones is even. Here number of ones is even. Here number of ones is odd. Yes or no? Okay, so can I say that neither odd nor even? Yes or no? Yes or no? See, for all f equal to 1 rows, number of ones in the input, that is sometimes that is sometimes that sometimes odd, sometimes even. Sometimes odd, sometimes even. So not linear. Yes or no? So you, if you check, the condition is not satisfied, so this is not linear. Is this clear? Please tell me. Let me know. Okay, let me ask you this. What about this function? Is this linear? Is this function f linear? Please tell me. Is this function f linear? First, what you will do, before checking linear, always what you need to do, make sure there is no dummy variable. Make sure there is no useless variable. First, remove useless variable. Is there any useless variable? First, remove useless variables. In this function, is there any useless variables? Okay, let's check with the help of K-map. You can check with the help of K-map. Just minimize x1, x2, x3. Okay, this is the area of x1. This is the area of x2. Okay, this is the area of x3. So now just check, is there any useless variable? Means just minimize and check. Minimize and check, is there any useless variable? First, remove useless variables. This is what you need to do. First, remove useless variables. Is there any useless variable here? See, a student is asking, removing useless variable means minimize. Actually, when you minimize, all the useless variables will be gone. So when you minimize, after minimization, the variables which are remaining, those are useful variables, right? Yes or no? When you minimize, then useless variables will be gone. A student is asking, what is useless variable? Useless variable means function does not depend on that variable. Function does not depend on that variable. For example, look at this variable. Look at this a. Look at this. Look at this function. In this, if you notice, this b is actually useless. This variable b is useless because function doesn't depend on b. Just minimize this. Okay, minimize. If you minimize, then what you will get? You will get f equal to a, right? So did you notice b was useless? Is this clear? Did you notice b was useless? In this function, b was actually useless. because when you minimize, then b is gone. Okay, so just make sure there is no useless variable. So when you minimize, then the useless variables will be gone. Let me just quickly check, is there any useless variable or not? Okay, 0, 1, then you have 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. Yes or no? Okay, so if you see what you will get, you will get this. What is this one? This is actually x3 x2 bar, x3 x2 bar. And what is this one? What will be this one? This will be x1 x3 bar. So actually there is no useless variable. Yes or no? Okay, actually you can see x1 x3 they are useful, x3 x2 they are useful, so no useless variable. That's it. No useless variable, right? Yes or no? Is this clear? Is this clear? No useless variable. Now nothing to worry. Now just check. Is this clear? Please tell me. Did you understand this concept that there is no useless variable? The function depends on x1, x2, x3. The function depends on all the three variables. You can see this function depends on all the three variables. For this function, there is no useless variable. Okay, now just check. Now check linear. Now check linearity. Now check f is linear or not. So what you will do to check f is linear or not? What you will do? A student is asking any technical name for useless variable. Yes, useless variable itself is technical name. Some authors, some authors they call it useless variable. Some authors call it dummy variable. Okay, dummy variable, useless variables. These are used in many research papers. These words, useless variable, dummy variable, these words officially, formally, these are used in research papers. Okay, is this clear? Now, anyway, let's check whether f is linear or not. Okay, so now you tell me, for all f equal to 1 rows, for all f equal to 1 rows, where are f equal to 1 rows? These are f equal to 1 rows. For f equal to 1 rows, what is number of ones in the input? What is number of ones in input? See, for all f equal to 1 rows, here number of ones is odd. Here number of ones is odd. Here number of ones is odd. Here number of ones is even. Here even. So sometimes even, sometimes odd. Yes or no? Sometimes even, sometimes odd. Correct? Sometimes even, sometimes odd. So this is not linear. Okay, so this is not linear. Is this clear? Please tell me. So not linear. Just apply the definition of linear function. A student is saying, is it necessary to remove useless variables? Yes, it is necessary to remove useless variable for linearity. Okay, to check whether a function is linear or not. To check linear or not. Okay, to check if a function is linear or not, useless variable removal is necessary. Okay, that is the reason I told you that before you check linear, first you make sure there is no useless variable. You don't have to minimize, you just have to make sure that there is no useless variable. Now, how to check whether you have a useless variable or not? For that, you can minimize. See, if you minimize, useless variables will be gone. After minimization, the variables that you get, the remaining variables after minimization, the remaining variables, they will be, okay, they will be basically, they will be useful. Okay, they will be useful. Is this clear? Please tell me, let me know. Okay, now let's see. So we have seen the definition of linear function, right? Now what the result number 4? The result number 4 is, this is your set x, that is f1, f2, f3. Okay, this is your set x. If every fi is a linear, if if every fi is a linear, then what we can say? If every fi is linear, then what we can say? Then we can say x is not functionally complete. Is this clear? Okay, if every fi is linear, then x is not functionally complete. Okay, you check, is this linear? Is this linear? Is this linear? If every fi is linear, then x is not functionally complete. This is our next result. Now let's see the next property to check. The next property to check, that is monotonic. Okay, that is monotonic. Monotonic. Okay, what is this property? Let's see the definition. The definition is, just try to understand the definition. This is actually very simple. Okay, what is this monotonic property? This monotonic property is like this. A function is monotonic. Okay, see, the definition is like this. A function is monotonic. A Boolean function f, okay, is monotonic. A Boolean function f is monotonic if and only if. See, the definition is actually very simple. It will be monotonic if and only if you increase a single variable from 0 to 1. Okay, see what I'm saying. This function is monotonic if and only if for every combination this would happen. For every input combination, this would happen, that if we change, okay, if we change single variable from 0 to 1, okay, if we change, or I can say increase, right? Okay, if we change single variable, please, this is important, that single variable. If we change single variable from 0 to 1, from 0 to 1 means we are increasing, right? Yes or no? Yes or no? We are increasing single variable. If we change single variable from 0 to 1, from 0 to 1, then function value, must not decrease. Must not decrease. Must not go from 1 to 0. Okay, must not go from 1 to 0, or I can say must not decrease. Is this clear? Let me know. See, the definition is actually very simple. When can I say a function is monotonic? A function is monotonic when for every input combination, if we change single variable, okay, remember we have to change single variable. You cannot change two variables. You cannot change two variables. You have to change a single variable from 0 to 1. Basically, you are increasing. Okay, you have to change single variable from 0 to 1. Then function value must not decrease. Means if you change from 0 to 1 single variable, if you change from 0 to 1, then the function value must not decrease. You are increasing, so this should not decrease. Is this clear? Please tell me. Let me know. Okay, so let's see. For example, let me tell you. Let me ask you. Consider this function, a function I'm giving you, like consider the OR function. Is this monotonic? Is this function monotonic? Okay, first you understand. See, the monotonic function you understand. For example, if you have a function f, let's assume you have a function f a b c. Okay, when can I say this is monotonic? It will be like this, a b c. Okay, this is your function. Now, if I change a single variable from 0 to 1, for example, let's assume here the function value is a 1. Okay, let's assume for this combination function value is 1. Now, if I change a single variable from 0 to 1, a single variable I am changing from 0 to 1, remember, then this function value should not decrease. I am changing a single variable from 0 to 1, then then this function value should not decrease. Means here, if you have 0, then this is not monotonic. Decrease happening, yes or no? This is decrease. So this is not monotonic. So f not monotonic. Is this clear? The definition is actually very simple. Okay, if you are changing single variable from 0 to 1, then the function value must not decrease. Is this clear? Please tell me. Okay, so let me tell you some more examples. For example, if you have a function f a b c, tell me, is this allowed? Just tell me a simple point I'm asking. Is this allowed? That, for example, let's assume here you have function value 0. I am changing single variable from 0 to 1. Here also I have 0. Is this allowed? Let me know. Is this allowed? I am changing single variable from 0 to 1. Then function value is not decreasing, right? then the function value is not decreasing. So this is allowed, right? Because the function value is not decreasing. So this is allowed. Is this clear? Let me know. Please tell me. See, the definition is actually very simple. So this is allowed. Okay. So very simple. Hope you understood. For example, is this allowed? I am changing single variable from 0 to 1. Okay. Okay. Is this allowed? Yeah, this is also allowed because function value is not decreasing. So this is also allowed. But what is not allowed? See, this is not allowed. If you change single variable from 0 to 1, then the function value decreasing, this is not allowed. Okay. For example, okay, if this happens, here let's assume function value is 0 and here function value becomes 1. Is this allowed? Is this allowed? Yeah, this is also allowed because function value is not decreasing. If I change single variable from 0 to 1, I am changing single variable from 0 to 1. Function value is not decreasing. So that is also allowed. Now let me ask you, A or B, is this monotonic? Tell me quickly. Is this monotonic? Please tell me. This A or B. Now, is this monotonic? Here you can easily see. See, for this combination, what is the function value? Just tell me quickly. For this combination, what is the function value for this combination? For this combination, function value is 0. Okay. If I change single variable from 0 to 1, then which combination I will check? With respect to this combination, which combination I will check? Single variable from 0 to 1. Remember, single variable from 0 to 1. Single variable from 0 to 1, right? Correct? Okay, so these two combinations you will check. You are going to check these two combinations. Single variable from 0 to 1, single variable from 0 to 1. So these two combinations you will check. Now you tell me, single variable is going from 0 to 1. Single variable is going from 0 to 1. Is the value decreasing? Is the function value decreasing? Is the function value decreasing? No, function value is not decreasing. Yes or no? Yes or no? So function value is not decreasing. So this is fine. This is also fine. Function value not decrease. Okay. Similarly, if I change single variable from 0 to 1, which combination I will get? With respect to this combination, which combination I will check? With respect to this combination, which combination I will check? Single variable 0 to 1. Okay, so this combination I will check. Similarly, with respect to this combination, I will check this combination because single variable from 0 to 1. Now you tell me, is the function value? What is the function value? The function value is 1. Again, this is not decreasing. Again, this is fine. Again, this is fine. Yes or no? So this is actually monotonic. Did you understand? Let me know. Is this clear? See, this is very simple, right? It is not complicated. It is very simple. What about A and B? What about AB? Is this monotonic? This is your truth table for AB. Now tell me, is this monotonic? Again, for this combination, the function value is what? The function value is 0. With respect to this combination, you will check which combinations. Single variable from 0 to 1. Remember, you are changing single variable from 0 to 1. Here, single variable 0 to 1, single variable 0 to 1. Okay, with respect to this, what you will check? You will check single variable 0 to 1. Now tell me, here the value is 0, here the value is 0, 0, 1. So is function value decreasing? Function value is not decreasing, right? So yes, this is also monotonic because function value is not decreasing. Here function value not decreasing. So here also this is fine. Function value not decreasing. This is also fine. Function value not decreasing. Fine. Function value not decreasing. Fine. So like this. So checking monotone or not, that is very simple. That is not complicated. What about A XOR B? Tell me. What about A XOR B? Let me know. Is this monotonic? 0, 1, 1, 0. Is this monotonic or not? You can check. This is the violation. Look at the violation. Here is the violation. See, for this combination, the function value is 1. If I change single variable from 0 to 1, then the function value is decreasing. Function value decreasing. So this is the violation. Yes or no? Function value decreasing. So I can say this is violation. So this is not monotonic. Is this clear? A XOR B, that is not monotonic. Understood? Please tell me. What about A implication B? What about A implication B? Tell me. This is the truth table. The truth table is 1101. Again, this is the violation. Okay, again, this is the violation. For this combination, function value is 1. If I change single variable from 0 to 1, single variable, if I change from 0 to 1, then the function value is decreasing. Okay, so this is the violation. So again, this is not monotonic. That's it. What about this function? Is this monotonic? Is it monotonic? Tell me. Is f monotonic? Please tell me. Is this f monotonic? The answer is again no. Okay, can you tell me why? The answer is again no. Why? See, very simple. Look at this. For this combination, the function value is 1. Okay, please focus here. For this combination, function value is 1. If I change single variable from 0 to 1, for example, look at this. If I change single variable from 0 to 1, what is the function value? If I change single variable from 0 to 1, single variable I am changing from 0 to 1, then the function value is 0. So this is the decrease. So there is violation, right? Yes or no? Did you notice this is the violation? So is this monotonic? The answer is no. Is this understood? Please tell me. Let me know. Is this clear to everyone? The definition of monotonic function, is this clear? See, very simple. Look at this. For this combination, function value is 1. If I change single variable from 0 to 1, other variables I am not changing. Notice, other variables I am not changing. I am changing single variable from 0 to 1, but the function value is decreasing. But function value is decreasing. So that is the violation. So this is not monotonic. Is this clear? Please tell me. So that's it. Okay. Now let me tell you the result. The result is this. This is your set of functions f1, f2, f3. If each of them is monotonic, then what will happen? If each fi is monotonic, if each fi is monotonic, then what will happen? Monotonic, then x is not functionally complete. Okay, then x is not functionally complete. Understood? Then x is not functionally complete. So this is the result. If every fi is monotonic, then x is not functionally complete. That's it. So these are the 5 properties. Okay, is this clear? So what is the theorem? The theorem is actually very simple. This is the theorem that, okay, let me tell you the theorem. The theorem is like this. See, this is your given set of functions. This set of functions is given to you, f1, f2, f3. The question is asking, is this functionally complete or not? So let me tell you. Let me tell you, x is functionally complete. Okay, what are the results we have seen? These are the results we have seen. If every fi, okay, if every fi is 0 preserving, then what will happen? Quickly tell me. Quickly tell me. If every fi is 0 preserving, then what will happen? Then x is not functionally complete. Yes or no? We have seen this. If every fi is 0 preserving, then x is not functionally complete. Or, or if every fi is 1 preserving, then what will happen? If every fi is 1 preserving, then also x is not functionally complete. Correct? Okay, remember, either this happens. If every fi is 0 preserving, then x is not functionally complete. If every fi is 1 preserving, then also x is not functionally complete. Okay, what is the third thing? Or what is the third thing? Tell me. The third thing, if every fi is self-dual. If every fi is self-dual, then what will happen? Then also X is not functionally complete. Yes or no? Then also it is not functionally complete. If every fi is self-dual, if every fi is self-dual, then also it is not functionally complete. Okay, what is the next thing? This is your set X. What was the fourth thing? If every fi is linear, if every fi is linear, then what will happen? Then also X is not functionally complete. Okay, clear? Remember, if every fi is linear, then also X is not functionally complete. And finally, if every fi is monotonic, then what will happen? If every fi is monotonic, then what will happen? Then also X is not functionally complete. Okay. Otherwise, if all these five things are not applicable, else, this is important, else, if all these five things are not applicable, else, otherwise X is functionally complete. Is this clear? Otherwise X is functionally complete. Let me know, did you understand? So this is important. If all these things are not applicable, okay, if all these five properties, five result are not applicable, else this will be functionally complete. X will be functionally complete. Did you understand? Please tell me. Let me know, did you understand? Okay, otherwise X is functionally complete. So very simple point. Again, I am telling you, this is the set of functions given to you. The question is asking, is this set of functions, is this X functionally complete or not? Then what you will do? Very simple. Check. What you will do? Check every fi. If every fi is zero preserving, each of them is zero preserving, then X is not functionally complete. If every fi is one preserving, then X is not functionally complete. If every fi is self-dual, then X is not functionally complete. If every fi is linear, then X is not functionally complete. If every fi is monotonic, then X is not functionally complete. Otherwise, X is functionally complete. Otherwise, X is functionally complete. Did you understand? Please tell me. Tell me the answer for this question quickly. We have already seen this. This set, is this functionally complete? Let me know. This set, is this functionally complete? The answer is no. Why? Just check. Each of them is one preserving. Yes or no? Each of them is one preserving. All are one preserving. Every fi, here, every fi is one preserving. Correct? Okay. Every fi is one preserving. So this set, so this S is not functionally complete. Understood? Very simple to apply. Okay, these are very simple to apply. So this post theorem you can very easily apply. If I give you any set of functions, you can very easily apply this post theorem. Okay, is this clear? Please tell me. So far, did you understand? Let me know. We have seen what is the definition of functional completeness. We have seen some examples. We have seen Nand is functional complete, Nand is universal gate, NOR is universal gate. Okay, then we have seen post functional completeness theorem. Five properties we have seen. Okay, so please tell me, did you understand? Let me know. This is the complete summary. Now, one misconception I want to tell you, and that is partial functional complete. Okay, many students they have this misconception. They think that this is a concept, partially functional complete. They think that this is a concept. Actually, this is a misconception. Okay, so what is partial functional complete? Partially functionally complete. That's not even a word. What it means, this is not even a standard concept. There is no standard resource, there is no standard book, there is no standard university, there is no standard resource which contains this concept, which contains this word partial functional complete. Okay, so remember, there is no standard resource containing such concept. So please understand this partial functional complete. This is not a concept. This is a self-made word made by some coaching teachers. Okay. So this is not a concept. Remember, this is a misconception taught by many coaching teachers. So if you have this misconception, so just forget about it. Remember, this partial functional complete, this is not a concept. Okay. This is not a concept in any standard resource. There is no standard resource containing this concept. Is this clear? You can see so you can see, I mailed to one of the IIT Kharagpur professor, Professor Indranil Sen Gupta ji. Okay, so I mailed them and I asked them, okay, just to verify, just to clarify. So you can see this is their reply. Okay, so this is their reply. As per my understanding, there is nothing called partial functional complete. Okay, there is no such thing as partial functional complete. Means this is not even a word, this is not even a concept, this is not even a thing. Is this clear? But still many students, they have this misconception, they use this word. Many students, they use this word because some coaching teachers, they are teaching the wrong concept, misconception. So anyway, so you don't have to use this word because this is not a concept. Is this clear? Okay, let me know. Now let me tell you one more important thing. This is final note and this is important. Okay, this is Boolean functions versus digital circuits. Please understand, functions versus circuits. Okay, now can you distinguish between functions versus circuit? Please tell me. Can you distinguish between functions versus circuit? See, functions, functions versus circuits, versus digital circuits, circuits and gates. Okay, for example, can you give me some examples of functions and can you give me some examples of circuits? Yes, examples of functions, for example, A and B. This is a function, this is a function, implication, this is a function, right? Yes or no? These are Boolean functions. Agree with me? Okay, these are functions. Yes or no? Very simple. So these are Boolean functions, right? And what are circuits? Circuits, for example, logic gates. Logic gates are digital circuits or not? For example, logic gates like AND gate, OR gate. Okay, yes or no? All these things. So remember, logic gates, these are digital circuits that you already know. I don't have to tell you. Logic gates, these are circuits. These are digital circuits. For example, multiplexer is digital circuit. Yes or no? For example, half adder, that is digital circuit. Okay. Decoder, multiplexer, these are digital circuits. Okay, and so on. So these are digital circuits and these are functions. Yes or no? Is this clear? So these things you already know. What is Boolean function? These are functions, Boolean functions, and these are circuits. Okay. The point that I want to tell you, what is that? Let me tell you the point. The point is, when the question is asking for digital circuits, okay, when the question is asking for functional completeness of digital circuits, then by default you can use 0 comma 1 signals. Okay, see, this is a note that for digital circuits, for digital circuits, for digital circuits like logic gates, okay, like logic gates, for digital circuits we can use, okay, by default 0 comma 1, by default 0 comma 1 are available. By default, by default, remember, by default 0 comma 1, these signals are available. These signals can be used. By default, these signals can be used. Is this clear? Because this is basically the low voltage signal, this is the high voltage signal. By default, these signals can be used. Okay, is this clear? Please tell me. Very simple. But remember, when you have Boolean functions, for Boolean functions, okay, remember when you have Boolean functions, so for Boolean functions, we cannot use. Okay, by default, we cannot use 0 comma 1. We can use only if it is given. Okay, 0 comma 1 signals can be used only if they are given. By default, we can't use them. By default, we cannot use 0 comma 1 unless given in the question, unless these are given. Okay, is this clear? Please tell me. This is a very important note. Let me tell you why. I will tell you why. But did you understand? Please tell me. So when you are discussing digital circuit in the gate question, if they are giving you digital circuit or logic gates and they ask you, is this functionally complete or not? Then by default, these signals, 0, 1 signals you can use. But if the question is talking about functions, if the question is talking about Boolean functions, then by default, you cannot use 0, 1 unless they are given to you. Okay. The same thing is given in the Charles Roth book also. This is the Charles Roth book. In this book also, this is given. You can see we will always assume 0, 1 are available as gate inputs. Okay. Is this clear? We will always assume that 0, 1, these signals are available as gate inputs. And let me tell you, the same convention is used by gate exam. In all the gate exam, gate CS, gate electronics, gate electrical, okay, gate instrumentation, in all the gate exam questions, this convention is used. Is this clear? Please tell me. This Charles Roth convention, this is used. You can see. Means with the digital circuits, if logic gates, multiplexer, decoder, okay, adder, all these things. So in the digital circuits, remember 0, 1, these signals you can use. But for functions, for Boolean functions, by default, you cannot use. Okay. Let me tell you what difference it will make. You might be thinking, sir, what difference it will make? Yes or no? So let me tell you two questions I'm giving you. Okay, consider these two questions. One question is this implication operation. One question is implication function. Is this is this boolean is this functionally complete? This implication function, that means a bar or b. Is this functionally complete? Tell me. Is this functionally complete? And my second question is implication gate is functionally complete. Implication gate is a functionally complete. What is implication gate? You can see implication gate. I can create a bar or b. This is the implication gate I can create. A bar. This is a bar or b. Yes or no? A bar or b. Now, a bar or b implication gate. Is this functionally complete? Tell me, is there any difference between these two questions? First of all, you tell me the difference between these two questions. Here I'm asking implication function, is this functionally complete? And here I'm asking implication gate, is this functionally complete? Tell me the difference between these two questions. Please tell me. Please tell me the difference. Here, remember, here because we are talking about functions, only this is what you can use. You cannot use 0, 1. But here, because we are talking about digital circuits, here because we are talking about digital circuits, so you can use 0, 1 by default. Is this clear? 0, 1, these signals you can use by default. This is the difference. Is this clear to everyone? Please tell me. Did you understand the difference? Here we are talking about Boolean functions, and here we are talking about digital circuits. Okay. So here you cannot use 0, 1 by default. You only have to use implication. Okay. But here you can use 0, 1 by default you can use. Okay. Now you can easily see. What about this? Tell me implication, 0, 1. You can check this is functionally complete. Why this is functionally complete? Tell me. Tell me. Can I say all are zero preserving? Let's apply the post theorem. Post theorem. Can I say all are zero preserving? Can I say all are zero preserving? No. This is not zero preserving. This is not zero preserving. Can I say all are one preserving? This is not one preserving. Yes or no? See, very simple. This is not one preserving because this is always zero. This is always zero. So this is not one preserving. You can see this is not zero preserving. You can see this is not self-dual. Why this is not self-dual? Tell me why this is not self-dual. See, implication, that is same as A bar or B. Okay. So tell me what is dual. Tell me what will be dual. Dual will be A bar B. Are they same? Are they same? They are not same. Yes or no? Is this clear? So this is not self-dual. What about the next? This implication, is this linear? This is not linear also. This is not linear. And what about monotonic? This is not monotonic. We have already seen. So now you tell me. Now you tell me. See, can I say everyone is zero preserving? Please tell me. Can I say everyone is zero preserving? No. Can I say everyone is one preserving? No. Can I say everyone is self-dual? No. Can I say everyone is linear? No. Can I say everyone is monotonic? No. So, so it is a functionally complete. Yes or no? So it is functionally complete. So you can apply this theorem very simple. This post theorem you can apply. If you don't want to apply post theorem, then also you can solve. Okay. If you do not want to apply post theorem, then can you create note from here? Can you create note? Please tell me. From here, create note. See, very easily I can create note. A implies 0. That will give me what? That will give me A bar. So I can create note. This is my note. A implies 0. This will give me A bar. Can you create or? Can you create or? Can I create or? I already have A bar. I already have A bar, right? Yes or no? I already have A bar. So I can create. Now I can create. I already have A because I already have A bar. So I can create or. This will give me A or B. Okay, so I can create not, I can create or. So this is functionally complete. Is this clear? Let me know. But if you have only this, now is this functionally complete? If you only have this, is this functionally complete? This is not functionally complete. Okay, why this is not functionally complete? You only have this, and this is one preserving. See, in this set, only one is there. Okay, only one is there, and this is actually one preserving. This is actually one preserving. So in this S, everyone is one preserving. In this S, only one function is there, and that is one preserving. So S is not functionally complete. Yes or no? So did you understand the difference between these two questions? Implication function, implication gate. Okay, the difference is this. Because this is a function, so you cannot use 0, 1 by default. Okay, because it is not given, 0, 1 is not given, so you cannot use. But implication gate, this is a digital circuit. Here you can use 0, 1 by default. Okay, this is the difference. Please tell me, did you understand? So this is what I'm saying. With the digital circuits, with the logic gates, with the multiplexer, all these things, by default you can use 0, 1 signal. But with the Boolean functions, you cannot use 0, 1. Okay, is this clear? Let me show you all the gate exam questions so far. For example, you can see this is not functionally complete. Okay, we have already seen why this is not functionally complete. Tell me. Here you have implication. Please notice there is implication, but still you can see this is not functionally complete because you can see all are one preserving. All of them are one preserving, so this is not functionally complete. But if you see this implication gate, this is functionally complete. Okay, look at this gate exam question. This is gate 1998 question. The question is talking about implication gate. Okay, question is talking about implication gate, and we have to prove that implication gate is functionally complete. Okay, so remember, because the question is talking about implication gate, the question is talking about gate, so you can use 0, 1. Here, basically, you have to solve this question considering this. Okay, this set is functionally complete. Okay, this set, this is functionally complete. So very easily. Is this clear? Similarly, you can see this gate electronics 2015 question. Okay, here also you can see gate are given to you. Okay, this gate, or gate, and gate, this implication gate. Again, this is your implication gate. Again, this is our implication gate. So again, in the question, implication gates are given to you. So 3 gates are given to you. The question is asking which of them is universal gate, and the answer will be this is universal gate. Is this clear? This is universal gate. Okay, because you can see this implication gate, comma 0, comma 1, this is functionally complete. Okay, so this is universal gate. The answer will be option C. Is this understood? Please tell me. I am showing you all the gate exam questions. Okay, so here you can use 0, 1. Very simple. Now let's see this question. In this question, can you use 0, 1? Just tell me. Can you use 0, 1? Here you cannot use 0, 1. Right. Yes or no? Here we cannot use 0, 1. Okay, you have to check this is functionally complete or not. This is functionally complete or not. This is gate computer science 2015 question, because this question is talking about functions. Yes or no? This question is basically talking about functions. This question is not talking about digital circuits. Okay, so here you cannot use 0 comma 1. For example, this gate exam question. Okay, tell me, is this talking about functions or circuits? Please tell me, is this question talking about functions or circuits? This is talking about digital circuits. Yes or no? This question is talking about gates or digital circuits, multiplexer gates. So here you can use 0 comma 1. So remember, 0 comma 1, 0 comma 1, 0 comma 1, 0 comma 1. Now you solve this question. Okay. Next, what about this question? Can we use 0 comma 1? Let me know. This is gate 2008 question. Can we use 0 comma 1? Okay, again we cannot use 0 comma 1. Okay, can't use 0 comma 1. Remember, you have to solve this question without 0 comma 1. Okay, is this clear? For example, this question, this is another gate exam question, gate 1993 question. Tell me, the question is asking only half adders are available. Only half adders are available. Show that they are functionally complete. Show that they are functionally complete. Here also 0 comma 1 you can use. Yes or no? Okay, can be used. And you can see this is a misconception. Partial functional complete. This is a misconception. There is no such thing. There is no such concept. There is no such thing. Okay, this is a self-made word made by some coaching faculties. Okay, they have made their own concepts or whatever. Okay, but this is not a concept. This is not a thing. This is not a standard concept. Okay, is this clear? So this 10 upward, this is showing you how much this misconception is, I can say, circulated. Okay, in the last many years, this partial functional complete, this misconception. On the YouTube, you just write on YouTube, you write partial functional complete. Okay, many teachers they are teaching this concept, and if you ask them show single standard resource, they cannot show. Okay, because this is self-made word. This is not a standard concept. Okay, anyway, so that's it. This is your chapter. Please tell me, did you understand? This is the complete summary of functional complete. We have seen everything in this session, every definition, every result, everything. Okay, I have told you everything that you need to know about functional completeness. Okay, remember, if a set of functions is given to you and the question is asking, is this functionally complete or not? Then there are two things you can do. Either you can use post theorem. If you don't want to use post theorem, then no problem. You can create and comma not, or comma not, Nand, nor, these things you can create. Okay. But basically, in your toolbox, you have all these things. Okay. I told you what is post theorem. Okay. 5 properties you have to check: zero preserving, one preserving, self dual, linear, monotonic. Okay, these 5 properties you have to check. Is this clear? Let me know. So everything, every concept, every result, everything I have told you in this session, please tell me, did you understand? Let me know. Did you like this session? This is the complete summary of functional completeness, every important thing we have discussed. Okay. Okay, thank you everyone.